Okay, it's time to begin. How's everybody? Good? Thank you for that email.
Welcome.
Okay, administrative stuff. Numero uno.
Número uno. Are you in Caribbean time now?
I'm only 2 minutes late.
I don't know, but for you it's like 20.
Who's that? Who's going to be 20 minutes late? Arthur?
Further.
No, but I'm saying that it's always sharp on time, so 3 minutes late for him, it's like a huge deal.
Lost in statistics, as a matter of fact.
Lost in statistics. Oh, that doesn't sound good. Or it does sound good. Okay, I finally am getting to the point where I've graded a bunch of binaries that have been long past due for about 10 years. And I started on the unequal sample size homework. And I don't know why it didn't occur to me before, but I remember we said the quiz was not right because we changed how we were doing things. And so I said, well, I'll just grade it from a submission. So we created a Dropbox. You guys submitted the Dropbox. And I sat down this weekend and said, I need to grade this and get it out of the way. So I graded all the other things. And on Sunday evening, I said, well, I'll grade a few of these and then I'll finish them up Monday because I work from home on Monday. And I got in and I started with the first one. I wanted to see how you guys had done it. So I opened just a couple of them to see if it was complete. And I said, okay, yeah, they're complete. That's good. I will now grade it using the earlier version. And I got into it, and then I realized that I needed to create the analysis the correct way so I could grade your work. I don't know why it didn't. I mean, it's obvious once I realized it. So I ended up spending a good part of the day Monday creating the answer key to be able to grade the assignment. And then I started working on it and didn't finish. So I will finish that and get that going for you. You have a holiday coming up next week, so there's no class next week. No assignments due next week. Yahoo. The only thing that would be useful for you to do, have you spent any time yet reviewing any of the videos and looking at the problem definition for the team project? Done any of that?
To be honest,
Not really.
Not really. Oh, okay.
Read the
I'll send an email to remind you of that, and I still have to create your teams. So we will get that done, and I'm going to have 2 teams of 4 and 1 team of 3. That's 4 and 8. That's 11. So that will be the 11 people that we need. With respect to the binaries, the one binary was the ANOVA on 0-1 data. That was one where I had created a data file. I created a data file that was in frequency format, and you couldn't use it. And I think right at the very last minute, I scrambled and created a new file. Although I did tell you how you could do it. One of the things that I found was that for some reason or other, for some of you, there was chunks of it incomplete, and I thought I had it written down here, but I don't. It might have been associated with the post hocs, I don't know, but I made a note to myself that I sent a note to you in giving you credit for it, and there was some option for you to resubmit for full credit. So if you got one of those messages on the 0-1 ANOVA, go ahead and if you want to resubmit, I think I gave you like binaries are worth 1 point, and they're extra credit type things. There'll be a score there for you, and I think I gave you like 0.5 and said if you do this, then you resubmit, then you get the other half point. If you're happy with that, just say, I don't want to spend the time messing with it, that's okay. But on the next one, the solutions for the four-way design cell coding, I am not sure why. It might have been me, but on that, on the initial spreadsheet, and let me see if I can pull it up. I don't know. Maybe I didn't. Let me pull up this guy. Okay, the first thing that you are supposed to do, and everybody did this, and I don't recall that there was any problems with this, was given this cell coding arrangement to go ahead and create values in columns A, B, C, and D, and that would conform with this pattern in the design cells. And then to use MVP stats to generate cell codes, which you can do, and it has instructions on the first one. As I recall, the first one in is the one that changes fastest. And then there was a formula to use to generate cell codes that was on another separate piece of paper that you can use. That is probably not so important for us in Excel, but it is important for us in R, because when we're using R, if you're going to generate cell codes, it does not make sense to take the design, copy it out into an Excel spreadsheet, and then to do the work there and bring it back in when you can simply just use the commands in R to generate cell codes. And I thought I brought a slice of paper with my notes on it, but I don't see it now, so I'll just have to create it on the fly, which is always, for me, a recipe for disaster, right? Trying to do stuff like that on the fly. At any rate, we'll do that. But everyone did that part, but for some reason, about half of you did not do the bottom part, starting here, in which the instructions were, assume that in the order that the cells are listed here, A, C, B, D, that A is varying fastest, C is varying next fastest, then D, then B, and then enter numeric codes into these cells that correspond to the cell codes. So as an example, I don't want to give it, and since about half of you did that, or about half of you did not do this, I think on this one I gave you zeros because I really want you to understand how to do this, because not next week, but the next time we get together, we have three-way ANOVA, and the issue of cell codes becomes really important. So you have to have a fluency with this. That's why I generated 5 additional of these things, in addition to giving you the codes and having you create the values for the variables in the columns. Then I wanted you to, using this coding structure, generate and fill up these codes. So I would like for those of you who, that again, it's your option if you want to. I think on these, if you didn't do this second part, I gave you a 0, I think, and said, please resubmit for full credit. If you don't want to mess with it, then that's okay. But giving you the option to do that, because I really would I think that there's a big benefit to doing this. And it's actually pretty simple. With this one up here, it asks you to indicate which one was fastest, second fastest, third fastest, and fourth fastest. Well, if you look at the numbering code, where if it goes from 1 to 2 to 3, what's changing fastest? Well, that's factor D. D is changing from 1 to 2 to 3. So D is fastest, okay. And then when we go to 4 to 5 to 6, so from 1 to 2 to 3 to 4 to 5 to 6, so what's changing? Well, then A is changing, so it's changing second. And then after that, we've got, come down to 6, then we go 7, 8, 9, so now B is changing from 1 or excuse me, C is changing from level 1 to level 2. So C is third fastest, and then B is last. And so by looking at this, figuring this out, and being able to put these in order, this down here is a trivial part. It would take you like 5 or 10 minutes to do it. But I want you to do it so you have a good sense of what is going on, and then you're good to go with respect to other things that you may need to do. And no, this was in the template.
I don't have that
I
one.
must have had an old version because mine didn't have any of that.
Yeah,
Yours
Yeah.
did not have that?
I have just
Didn't
the
have it
top
either.
section.
I was wondering why half would do it and half would not do it. Okay, I will email this to you, this template to you tonight.
And yeah, would you mind just resending the instructions? Because the instructions I had lined up perfectly with what was I taught. But
And I think that's the same.
oh, it is.
I will double check.
Okay.
And that's why I brought this.
I didn't feel like I was missing anything, I guess.
Yeah, and because it kind of surprised me because you guys almost always do everything that I ask you to do, silly as you are. But and that's why I couldn't figure out. That's why I thought maybe there's something that I did wrong that I gave you incomplete instructions or something. But
Yeah, I'm looking at the one on the website. It doesn't have that.
so now I'm wondering how some of you got the right one. That's what makes me wonder.
Is the
Oh, you guys are those are the cheaters. Then they're getting it from last semester, and then they're just using the answers from there. No.
D2L the same for both distance and students here?
Would what?
Is D2L the same web page, the same thing for distance students and for us?
Oh yeah. D2L is the same. I will check the instructions and the template to make sure that they are.
I'm wondering if one was
What's that?
under the grading. Sometimes you can download it from the grading tab, and sometimes you can download it from the content tab.
Yeah, it needs to be in the content tab. I've got to fix that and make sure that it's there so that next year I don't have the same problem, because I'll never remember next year to fix it. You got to fix them now as we go. But what I do want to do is to spend a couple of minutes with generating the formula for doing these. And the best way to do it is to just start with, let's see. Oh, that's okay. Let's say we have A, B, and then I'm going to come back and add C. 1, 2, 1, 2, 1, 1, 2, 2. Okay, now if we let tonight's just going to be kind of a casualish night, kind of get us all caught up to where we're at and to organize some things for us. So if A is changing fastest and then B, and then we'll do it B changing fastest then A, then the cell codes would be A changing fastest 1, 2, B changing 3, 4. If B is changing fastest, it would go 1, 2, 3, 4. Okay? And of course, you can always draw yourself a little grid over here, A, B, and lay them in there. So with A changing fastest, it would go 1, 2, 3, 4, A, 1, 2, B, 1, 2, A, B, B changing fastest, it would go 1, 2, 3, 4. Sometimes it's easier to just see it in cells than it is to do it this way. But when you're doing, the reason that I'm doing this for you is because, or to you, is because when you get out of this class and you're on your own and you're doing your own research, you got to create your own data file. You got to start from scratch and go with it. And these kinds of tricks and tools are very, very helpful for you to go. Now, it is true, if the data file is small, then you can simply just put these guys in and then create your cell codes just by looking at them and just typing them in as you go. But when you get a lot of data, then things get complicated fairly quick. And remember, within each cell, there's always n specimens, from 1 to n specimens. So these things can grow fairly long. And you found that out when you had to create your file for the homework assignment for the wafer fabrication, the unequal n sample size one. You had to take that data file and expand it out, and it was in like, what, 2,000 rows? Something like that. And so to try to do it manually, just too time-consuming, too tedious, and very much error-prone. So you need to be able to use formulas. And so let's just use some coding. The formula works with fastest changing variable. Let's discover it. Let's start with A. So we're going to start with A, and then we're going to add to that B minus 1 times the number of levels of A. Okay, so when A is 1, so for the first condition, A is 1 plus B as the number of levels of B. B, that's okay, B minus 1. So B is, for this cell right here, A is 1, B is 1. So A is 1 plus 1 minus 1 is 0 times the number of levels of A, which is 2. So that just gives us a 1. So if we use that formula, then what happens for this cell? Well, in this particular case, A is a 2 plus B is a 1 minus 1 is 0 times the number of levels of A is 2 is a 2. Okay. Now when we look at this cell, A is a 1 plus B is a 2. So 2 minus 1 is 1 times the number of levels of A, which is 2. So that's 1 plus 2 equals 3. And then the last cell is A is at 2 plus B is at 2 minus 1 times 2. That's 2 plus 2 times 1 is 2, which is 4. And so this is the cell sequence, which is that one. And that's what happens when A is listed first. Now let's do the same thing with B listed first, plus then it's the other factor minus 1, its level, times the number of levels of the factor that's on the front side. So now let's go back. I'll do this in a different color now. So now we're going to look at this one. So A is at 1 and B is at 1. So 1 plus 0 equals 1. And now let's look at the second cell where A is 2, 2 minus 1 times 2, plus B is at level 1. So we have 1 plus 1 times 2 is 2. Plus 1, that's 3, okay. And now for this cell, A is at 1 minus 1 times the number of levels of B plus the levels of B, which is 2. 2 plus 0 equals 2. And in the last cell, B is at 2 and A is at 2 minus 1 times number of levels of B, 2. So this is 2 plus 2 equals 4. And this, of course, is the code right there. And those are the only two codes that are available. So this little formula, write it down. I've got this thing written down a dozen places and in a dozen files, and I can never, ever find it. I always just have to sit down and rederive it. Just have to go at it again. Pardon? Yeah, then it's actually kind of a cool thing. Now you can create this kind of formula in Excel, and certainly you can do it in R. All you guys are getting skilled enough in R to do it. So let's now take this up a level. Now let's say A has 2 levels, B has 3 levels, and C has 3 levels. 1 and 2, 1, 2 and 3, 1, 2 and 3. So let me draw a picture of the design. Well, this is kind of cool. Okay, let's say that this is A1, A2, B1, 2, 3, C1, 2, 3. This is B1, 2, 3, C1, 2, 3. So we have it laid out like that. And I did it this way so I wouldn't have 3 of these spread out across. If I did, I could have done it as a 2 by 3, and then have 3 of those. So I could do C1, C2, C3. A is at 2 levels, so that would be A1 and 2. And then across the top we'd have 1, 2, 3. B1, 2, 3, A1, A2, B1, 2, 3, A1, A2. I could do it that way. It doesn't matter how you do it. Now, when we do this, as soon as you get a second and a third factor, or a third and a fourth factor, it gets a little bit complicated, the formula. So we start with, let's just see what happens. Let's start with A, and we know that we have to take the number, we have to take A minus, or A plus B minus 1, and then this guy is multiplied by the number of levels of factor A. Now here's where it gets dicey. Then we have to add to that C minus 1 times the level, the number of levels or combinations of the terms, the factors that come before, the number of A, B levels. Okay? So in this arrangement, A has 2 levels, B has 3, so the levels of A is 2. The levels of A times B is 3 times 2 is 6. I don't want that guy to be sitting right there right now. Okay, so let's just start and go through it. Let's say that I want them to go in this order: A fastest, then B, then C. So this is what's going to happen. When I do this, A is going to change from 1 to 2 before anything else changes, and we're going to start at the 1, 1. So it's going to go cell 1, 2. You see why? Because this is A1, and this is A2. So A is going to go from 1 to 2, and then B is going to change. So then we're going to go to B, so B changes from 1 to 2 after A changes. So this is going to be 3, that's going to be 4. And this is going to be 5, that's going to be 6, and we run it to the end. And then C changes from C1. Notice that all this is all C1, this is all C1. So then it's going to go 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's how, when I write the formula this way, this is what is going to happen. Now let's just go through the code so that you can see it unfold. Okay, so when A is at, so the first cell right there, A is at 1, B is at 1, times the number of levels of A is 2, plus for this cell, C is at level 1. So that's going to be, actually, I ought to put the numbers in there. Let me do that. Okay, B is at level 1. C is at level 1 minus 1 times 6, because A times B is 6. Now let's do the work and see if what the cell code turns out to be. 1 plus 0 plus 0 is 1. Okay, good. Okay, now let's go to, and let's just go to that cell now. Okay, so that's A is at 1 plus B is at 2 times 2 plus C, this is still C1, 1 minus 1 times 6 is equal to, okay, so that's 1 plus, B is a 2, so that's 2 minus 1 is 1 times 2 plus 1 is 3 plus 0 is 3. Well, sure enough, it worked. Okay. Now let's try that. Let's see what that cell code is. That's a C3. Okay. And that is a B3. And it's an A1. So A1 plus 2 times 2 is 4, that's 5, plus 2 times 6 is 12. 12 and 5 is 17. Okay? And let's just do one more just for fun. This guy over here. Okay, that's an A2 plus, and it's a B2, 2 minus 1 times 2 plus, and that's a C2, 2 minus 1 times 6 equals, okay, so 2 plus 1 times 2 is 2, that's 4, plus 6 is 10. Okay? This is what I end up having to do every time. So even though, but the point is, even when we want them to go in the order that I have them in there right now, then this formula with A varying fastest, then B, then C, that creates that pattern. And when you do that, copy that formula all the way down, it just fills them up for you. So you've got to know how to do this, I think. Okay, let's do... I could have just done it down here. Let me do that. Okay, so let's say that I want it to be filled this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So what's changing fastest when I go from 1 to 2? What's changing fastest? B. Very good. See, I'm helping you do your homework assignment.
Right, see.
But that's all right. I'm not trying to hide anything from you. I'm trying to make sure you learn this stuff. And
can you hide the keyword, by the way?
And also what's that?
Can you hide the keyword talking about writing?
Yeah. Okay. So now, in this particular case, B is changing fastest, right?
We'll see.
Oh, I'm sorry. C. Thank you. You guys have already learned you have to keep an eye on me, right? C is changing fastest from here to here. C is changing. Okay? 1 to 2 to 3. So C is changing first, and then what? 1, 2, 3, then 4. So that's A. Then A is changing. And notice we're going to multiply this times the number of levels of C, the guy on the front side. In this case, that's 3. then the thing that changes last is B. So after we go to 6, then we come back to 7, 8, 9. Okay, so then B changes last, and that's going to be that number of level minus 1 times the number of levels of the combinations of the factors that precede it. In this case, it's C times A. C times A is 6. Let's see if it works. Okay, let's pick on this cell right there. I want that cell right there. Okay, so that's a C2 plus, it's an A2, levels of C is 3, plus, and it is a B2. Okay, 2 times 3, plus 3 times 1 is 3, plus 2 is 5, plus 1 times 6, 5 plus 6 is 11. Worked out. Okay, let's just try one more just for fun. Let's try that one. That is a C3 plus A1 plus a B3. Okay, so 3 plus 0 is 3, plus 2 times 6 is 12, 12 and 3 is 15. I did it. It worked. Now, let's do one more. And we'll put the numbers in up here. But this time, I want B to change fastest, and then C to change, and the levels of B is 3. And then add to that A, and prior to that is the levels of B times the levels of C, which will be 9. Okay, let's see what goes in this cell right here. Okay, that is a B2 plus, that's a C2, oops, 2 minus 1, times 3, plus that's an A1. Okay, 2 plus 3 is 5. Okay, so that looks like it's going to be a cell 5. And let's see what happens down here when they're in this order. Okay, so that is a B3 and a C3. Oops. And an A2. Okay, 3 plus 6 is 9, plus 9 is 18. Now, there's always something that we know. The first cell is 1 and the last one's the combination. Okay, but now let's see if I've actually done it correctly. So let's go to green. Okay, so B, we said B is changing fastest. So we start here with cell 1. B is changing fastest. B is going to go from 1 to 2 to the cells 1 to 3 as B changes. And then C is going to change. So now we have to hop into second column. So now C, once I complete this guy, then C is going to go to the next level. So that's going to be 4, 5, 6. And then C is going to go to the next level, 7, 8, 9. And then A changes last. So then it's going to go 10, 11, 12, 13, 14, 15, 16, 17, 18. You want to do a double check? Say yes. Okay, we'll do a double check. Let's double check with this cell right there, lucky number 13. Okay, that is a B1, and it is a C2, and it is an A2. 1 plus 3 is 4, plus 9 is 13. So now, if you've done any computer programming, this is all fairly routine stuff, but not everybody has had some, but you are learning to use R to generate these things. So having this just having this formula. Now, what if I had a fourth factor, D? Doesn't matter how many levels, say 4 by 2 by 3 by 6. Now that's a big complicated thing, but it doesn't matter. Which do you want to go first? D, okay. D plus C minus 1 times the number of levels of D plus the next factor, whatever factor you want. If you wanted to go D, C, A, B, then you would write, let me do it up here. I don't know, can't even figure out what I want to erase. Let me erase this. If I wanted to go D, C, A, B, then I'll do D, then C, then A, and then B. Now, here I put the number of levels for the factor on the front side. Here, I have to multiply this by the number of levels of the two factors on the front side, CD. And on this one, then I have to multiply this by the number of levels of DCA. Now, in this particular case, the number of levels of D is 6. The number of levels of CD is 18. The number of levels of B is 2. So that's 2 times 18, that's 36. And it just goes. Automatically, it just goes. And it doesn't matter. You can pick how you want it to go. See, most people will say, well, look, I'd like it to be, think of it this way. When I start creating my columns, a lot of people, and me included, I like to see the factor that varies the fastest be on the end. So I'd have a whole bunch of 1s and a whole bunch of 2s. Then I have some B1s and some B2s. Then I have some C1s and some C2s. And then within this I have D1s and D2s, D1s, D2s, D1. So D would be changing fastest. So I would write these as, I almost did it. If I just flip these around, I'd have it. Now, other people like to write these the other way so that they have 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2 in the A column. And then in column B, I have a 1 for those two, and a 2 for these two, and a 1 for these two. And then when I go to C, I have a 1 for all of those, and a 2 for all of these. And then when I get to D, I have a 1 for all of those, and then a 2 for everything down below. So you can create these things any way that you want. Personally, I like to do it this way because when we get to 5620 next semester, we're going to learn something called a fractional factorial design, and the orthogonal arrays that are generated are always in this order rather than this order. But the point is, this is the important point. Doesn't matter how you do it, so long as this was here last week. Doesn't matter how you do it, so long as when you do it, the conditions that you set up are the conditions that drive you to manipulate, because the A, B, C's, and D's are treatment factors you're going to be manipulating at different levels. And you want them to be systematically manipulated so that when you set that condition, then you're going to collect data on all of your specimens in that single condition. Then for the next condition, you're going to randomly select specimens in that condition, and so on all the way down. So It doesn't matter how you do it, as long as you do it correctly and are consistent, you'll always get proper and good results. And we'll see more of that later on. But this kind of thing of having a fluency with cell codes is an important thing. And I'm really toying with the idea of having this particular binary be done way early in the semester, because it might then help you as we start getting into some of these more complicated designs as we come along. But so now, knowing based on what I just did over here, by filling numbers in these cells, now you know how to do the bottom part of that remaining chunk of that binary, and so it's an easy way for you to pick up some credit, give your brain. You can exercise your brain while your brain is relaxing. That's what I think. Yeah.
The screen.
This one?
Yeah, the final term, the levels of D multiplied by the levels of C by the levels of A. Is that what you have there?
Oh, yes, that right there is the number of levels of D.
Yeah.
And D first, then C, then A. D, C, and A. It's always the number of levels of the factors that have come before.
Is that what you have equating to 36?
Is that what I'm equating to what? 30? Yes. Yes. D had 6 levels, C had 3 levels, and A had, it's not 36.
I was just making.
It's going to be 3 times
72.
6 times 3 times 4, 18 times 4. What does that turn out? 72?
Yeah.
Thank you.
Yes, sir.
Now, obviously, when you start getting into bigger things like this, this is the kind of stuff that would help you, Arthur, with the stuff that you've got, with all those wacky factors that you're pulling in. Okay, so that's the binary. I will, after class, I will double check the template and the instructions to make sure that, and then I'll just email them both to you. I'll post them as well, but I'll email them to you. Then you'll just have them directly, and you can go home tonight, get a bowl of ice cream, sit down, and while you got one eye on the TV, you can have one on the screen, and you can type with your left hand and do this. It'll take you just a few minutes. Okay, how's that? Okay? Okay, what I want to do now is basically a course review. Because I'm laying the foundation for you to do the reading of Unit 10, which is the last unit, and I want to have it in a context for you so that you won't be, I don't know if I'm going to get to, I'm not sure that I even have to, let me take a quick look. Oh, I didn't bring it. It's in the other, I'll go on the break and get it. Just to make sure, I don't know that I have to do very much in that to put our code into it, but I'll do that over the break, and you'll have it in time to, prepare for the next IU prep quiz. Okay, so in this class, two-way designs, factors A and B. When we started out with Unit 1 and Unit 2, we had, let me do it this way. We started out with two-way, quote, fixed designs. Now, we didn't use the word fixed. We didn't say fixed back then. We just said we have two factors, and here we go. But it turns out that those two factors, A and B, were both fixed. The thing that was new that we learned is that anytime you have two or more treatment factors in a design, you have to allow for the possibility that there will be an interaction between those two. I'll do it this way because you will see this notation in the notes, in the text material from time to time, and I want it not to be a mystery to you. IAB, interaction AB. Personally, I just like to write the letters AB together. And with this, we basically learned the basics of what it meant, the source table, the A factor, the B factor, the interaction effect, how to look at the source table, how to generate it in the ANOVA, why it would be done, how it would be done, what an interaction is, how do you interpret an interaction, etc. Now, in every factor, in every design, we always have, in two-way designs, we have two treatment factors, A and B, plus there is always specimens. And even back then, we didn't say much about it. I just said, look, this is a fact. We always have specimens. Specimens is a random factor, and it is always nested within the AB combinations. We learned that early on, and that's what got us going. See, we had already gone through one-way ANOVA with multiple levels of one treatment factor. We understood that we had to do post hoc analysis in that situation, so the idea of post hocs carries over. The only difference here is you have three things to look at, A, B, and the interaction, not just one thing. And we also learned that the A, the B, and the AB interaction are all rolled up together in one big model that you could take those pieces and string them out into a one-way, where the one-way would be with the number levels of A times the levels of B, that many cells on a one-way. And as a matter of fact, we use that little trick to help us in the post hocs in some cases along the way. Unit 2, we took all of this, the same stuff, and we did, the big deal here was post hocs. Okay? And it boils down when you turn up the heat and you let it roar and boil and you stir it and you turn the heat down, what bubbles to the top is basically this. There's an equal variance versus unequal variance methods. It boils down to two issues. One, and two, the number of comparisons. And the number of comparisons breaks down into two really simple things. All pairwise or a few pairwise. That is all pairwise or not all pairwise, basically. And we find that it's convenient, although not always recommended, when we're doing all pairwise, when you have unequal variances, it's Games and Howell. If you're doing all pairwise and you have equal variance, that's Tukey. Now, the reason that let me back up and just say, most software that's designed has the basic ability to do an analysis with factors that are fixed. Oh, by the way, fixed and crossed. That's where we started. And as soon as we say crossed, then that's what gives rise to the interaction. And you already know that. All software that started out to be able to do analysis of variance started out with one way. And since the underlying assumption of ANOVA is homogeneous variance, and if you have equal variance, the denominator of the F ratio is the within variance, which is the average of the variances within the cells. And therefore, if you take that variance within the cells as the average variance and use that term, you can then easily create t-tests for pairwise comparisons. I'm not going to go into that. If I start, I'll just, and we don't necessarily want to do that. But I will say this. You know from 5005 that's the formula for the t-test. This guy is distributed as t with n1 plus n2 minus 2 degrees of freedom. Now, if, let me actually make it technically more correct. If sigma squared 1 equals sigma squared 2, then S squared 1 and S squared 2 are estimating the same variance, sigma squared. Does that make sense? So if we pool S squared 1 with S squared 2 over 2, we get an S squared P, a pooled variance, which is the within variability. It's the average of the two within cell variances, cell 1, cell 2. So we can now write this denominator this way. S squared pooled times 1 over n1 plus 1 over n2. That is if that's true. Now, if variance 1 does not equal variance 2, then you ought not, don't do that. Then what you have to do is you have to maintain this representation so that S squared 1 is estimating sigma squared 1, S squared 2 is estimating sigma squared 2. You have to keep them separate. That's the difference between the equal variance and the unequal variance t-test. Now, the fact of the matter is, as long as n1 equals n2, this denominator is going to be the same. Doesn't matter how you do it. But if the sample sizes are different, then this thing can take on very different values. And this guy is the one that is distributed as t with n1 minus n2. This guy, however, is distributed as, I'm going to write it backwards, t with degrees of freedom equal to degrees of freedom asterisk, which is the big, hairy, modified degrees of freedom formula that Satterthwaite developed. Now, the reason I'm mentioning this now is because in Unit 10, we learned about Satterthwaite. We come back to Satterthwaite for a bunch of stuff that we're going to do. Okay? So, with that, this is under the assumption of homogeneity of variance, equal variances, and this guy has a new name. We can call it mean square within. And take the square root. That's exactly what this is mean square within, the average variance within. And so, because of this relationship of t-tests to the ANOVA, and Tukey didn't stumble upon, but he developed his method based on this understanding and said, I will develop for you a procedure that will give you type 1 error rate protection alpha to do all possible pairwise comparisons, provided that they're of this format. Well, there were those who said, well, yeah, but what if, yeah, but what if the variances are not equal? Then what do we do? Well, along comes Games and Howell, and they said, well, we'll take that on. It's not a problem. So they figured out the machinery behind the works to do the calculations to give you these unequal variance procedures. And that's why in fast TM, just think about this. In fast TM, when you use the Tukey, all you have to do is you have to enter the mean square within, which is called the mean square AET, right, which is within, the degrees of freedom within. You need to set a significance level alpha, and that's it. And then just check the Tukey box. And up at the top, you have to enter the means. Variances, don't have to do it, but you do have to enter the sample size. However, if you're going to do Games and Howell in fast TM, I'm hoping that I'm doing things that are familiar to you, but I'm putting in detail that you say, oh, now I've got it. I think I understand this. So with this guy, over on the left-hand side, the only thing you have to do is to put in alpha and the mean square AET. It's not even there. The degrees of freedom for the AET, it's not even there. But up top, you have to put in the means, you have to put in the variances, and you have to put in the sample size. Because the Games and Howell procedure, when you do it, is going to go in here and pull the means for the numerator. It's going to pull the variances, the individual variances into the denominator and do those tests. See, when Tukey does his work, he goes, well, let me write the x bar 1 minus x bar 2, and then this is the denominator downstairs. It's really just a t-test. Under the hood, it's all a t-test. So when Tukey does his work, he goes up here and gets the means and puts them in the numerator, and then he goes over here and gets the appropriate error term, puts it down here, and then he goes up and gets the n and puts the n's in here. That's why you don't have to put variances in, because it's using the common pooled variance, which is assumed based on equal variances. That's why we have to do shape, then variances, and then means in our analysis sequence. Okay? Now, we did learn that, yeah, there's some other stuff that can be used intermittently, Bonferroni. And Bonferroni is what we use when we use only a few pairwise comparisons. And Bonferroni controls alpha by taking alpha divided by C. C is the number of comparisons you're going to do. And it just rolls out from there. And, oh yes, there is an equal variance and an unequal variance Bonferroni version. And anytime you do unequal variances, so this up here is for unequal variance, Tukey down here is for equal variance. Anytime you have unequal variances in fast TM, you have to enter what those variances are. Very straightforward. Okay, from there, we went to unit number 3, which was a two-way fixed crossed blocked design. A, B as treatment factors, plus C, the blocked variable. And in this design, since A and B are crossed, we could have a possible A-B interaction, but no, and now think about this, anything with C in it, CA, CB, CAB, this stuff goes into the residual and gets combined with the within error. Now this ought to make a whole lot more sense now that you're hearing it tonight than it did when we first got into Unit 3. But if you go back, you say, oh, yeah, okay, yeah, I've got that. And when we talked about a blocked variable, we said a blocked variable, by definition, the research question is, what combinations of A and B give me the best performance across, regardless of the levels of C? So I want to be able to generalize across. So by definition, there cannot be an interaction that I'm concerned about. So any mathematical manipulations that are oriented towards an interaction are not put in the source table, they're put in the residual as random error variability that we have to overcome, that the treatment factors have to overcome in order to be able to generalize across that blocked variable. And everything about the post hocs is the same, with one small exception. The design cells A by B by C. Design cells. There are AB treatment factor combination cells, but there are A times B times C design cells. The design is a blocked design. The blocked variable is part of that design, and therefore it gets credit for being part of what makes up the, quote, design cells. Okay? And we always must calculate variances. Oh, let me back up. We do normality and calculate variances within the design cells. That's just how we do it. Because we check normality within those cells because the treatment factors are going to be generalized across them. We calculate variance within those cells because we don't want, we've done this before. Let's just say we have one group and we have the blocked variables C1, C2, C3. Now let's assume that I have these values, 1, 2, 3, 5, 6, 7, and 12, 13, 14. Let's just talk ranges. 2, 2, 2. The amount of variability within the cells is 2 units. If I look at the amount of variability, so here the average within cell variability is 2. If I look at this whole thing, the variability here is from 1 to 14, or 13 units. Why is this variability 13 and this variability 2? Well, it's because this guy's average is 2, that guy's average is 6, this guy's average is 13. So 2 to 6 to 13 is variability in the means of the treatment of the blocked variable C, and we don't want to calculate variances across those levels, because if there are differences, then it's going to inflate the variability from 2 up to 13 in this particular case. So we have to have within cell variability, and then when we're going to do any post hoc analysis, then we're going to average the within cell variabilities so that we're truly keeping the treatment, the blocked factor C, out of everything. We're taking it out of the denominator, and we're taking it out of the cells, and we're putting it on the source table on a line all by itself, which we do not evaluate for significance. We don't care. We just don't want it contaminating, confounding either the A main effect or the B main effect or the residual variability. See, this guy right here is in the residual variability when I do that. But I want to pull the C out of there. I want to pull the 2, 6, and 13 out of there. And when I do, then I'm left with 2, 2, 2. So that was the only thing that was new there. And everything about post hocs was the same, except that the proviso for doing the post hocs, the within cell variances, if you had to have dispersion analysis, says you have unequal variances, then you have to deal with those average variances within the cells. Very straightforward. Unit 4. Sample size calculations for two-way designs. That's all I have to say about that. Unit 5. Two-way, fixed, crossed, I'm sorry. Two-way, fixed factors, nested. Nested treatments. Now notice, this nesting is not the same as this nesting, because in all of these designs, here, and here, and here, specimens is a random factor that's nested within the combinations of the treatment factor. And for the block design, it was nested within the design cells. Let me put design cells up there to make it explicit, within the design cells. The only thing that's different now is we have A and B within A, no interaction. As a matter of fact, this guy is made up of B and A by B interaction. Now, we learned it back then, but we were just reintroduced to it a week or so ago when we had the nested mixed model design. We went back to the nested idea. And this little thing right here is magic because, see, up to this point in time, for that design, this design, up to this point right here, we had the regular plain old AOV, analysis of variance, AOV, R command, do it, comes right out. And as a matter of fact, when we did this guy, there is a nested notation in R. It was AOV, criterion measure, A, and then this symbol, and then AB. Oh, no, I'm sorry. Sorry. it's A plus AB. I don't like the way that that's done, but it's just the way that R does it. I like A and B within A, but this is read A and B within or subordinate to A. Okay? And all during the time we were doing all of this was AOV, criterion measure, A asterisk B. This one was AOV, criterion measure, A asterisk B plus C. For the blocked design. Now down here, it's AOV, criterion measure A plus the nested term, and this nested term is the summation of A plus AB if you're going to do a two-way crossed, all factors fixed and crossed. And of course, that's a phrase you have come to appreciate because that's how we have learned to do the analysis of these other more recent designs. And yes, there are post hocs. And the post hocs are exactly the same as they are above. It's just that the hypotheses are directing us. And this one, we have to do A, and then we have to do B within A1, B within A2, B within A3, and so on. This is a decomposition of that term. The only reason we do that is because it's perfectly consistent with the hypotheses that we're going to test. But when you think about it, doing these analyses right here, these conditionals, is what you would do if you had a significant interaction, you wanted to break the interaction down. One of the things we learned when we did our post hoc analysis is if there is an interaction, you have to break the interaction down by looking at the levels of one factor, quote, within each of the levels of the other fixed factor. And you have to do it A within B, and then you have to do it B within A in order to understand everything about A and B. Not much new, mysterious, or difficult there. Then we moved on to Unit 6. Unit 6 was two-way, fixed, crossed, unequal in. And again, we always have specimens, which is a random factor nested within AB combinations. Or better yet, design cell combinations. That's always true. And when we did this design, there was, if we have anything significant, we do have to do post hoc analysis. That's true. For this guy, however, you have A by B. You're going to run the, this is where we first learn that we take the criterion measure as a function of A by B. They're crossed. But in this particular case, we had to do it with the linear model and save this linear model because with that we had to do ANOVA on this, let's call it analysis out. And we had to tell it type 3 sums of squares. And so the stuff that was magic here is we had to use the CAR package. P-C-K-A-G-E. We had to use the CAR package. We had to set contrasts. Oh, contrast, I'm sorry. That's a period right there. And then we also had to do contrast poly. And this was under options. Options, this guy. And we had to set those contrasts in order to get type 3 sums of squares. And the only way we could get type 3 sums of squares is by using the LM function and the ANOVA output display function. And you said, well, why are we switching to LM? Well, because that's what we have to do to get these things. Well, why didn't we do it before? We could have, but it just seemed logical to me to start and go with AOV because it stands for analysis of variance, and that's what we were doing. So that's my weak and limp justification for doing what we did at that time. The good news is the syntax for linear model, LM, is exactly the same syntax as for AOV. With that, yes, there are post hocs. The same, everything that we learned about post hocs way back here for equal and unequal variance, for all pairwise and part, is all tied up in what we learned earlier. Nothing is different here. The only difference here is we have unequal sample size that we have to take into account when we aggregate and roll things up to do our treatments. After we left IU6, and this is the one, by the way, I am not quite halfway through grading your submission. I was explaining at the beginning of class that I realized that I could not use my old solution set. I had to actually do the analysis so that I could know what you were doing the right thing using the R commands. So I did that. Okay, then, number 7. Two-way random crossed design. When we say random, A and B are both random. Since they're crossed, it implies we can have an interaction, which is also random. The thing that is new here, the big new thing, is the appropriate error term for A and B is not equal to the AET used for AB. And as a matter of fact, AB is the error term for these guys, and the within, or you and I the software likes to call it residual, is the appropriate error term for AB. So we learned that was something new that was very different as soon as we introduced random factors into the arena. Everything beforehand, from IU6 and above, there was only one AET. AET was equal to the within cell variability. Even though the software calls it residual, that's what it is. It's the variability within the cells. That's the random unexplained variability. When we get into random factors, this guy is no longer the error term for everybody. It's the error term only for the interaction, but the interaction is the error term for A and B separately. So that was one thing that was new. Number one thing new. And number two thing new is the post hocs. Post hocs. Post hocs for random factors is the estimate of the variance for the factor plus the interclass correlation, that is the percent of explained variability, for that factor. Those are the post hocs. Always, but minimally. If you meet, because the factors, with these random factors, we're trying to do something different in terms of the hypothesis. We're trying to quantify the amount of variability that we can attribute to the random factor to know how much variability is coming at us as a result of it. With a fixed factor, we're interested only in identifying the factors that we have. We're only interested in those factors. We're only going to generalize to those factors, so we want to find out who is best. The idea of who is best in the levels of a random factor makes no sense. So we had that one additional distinction, that is the post hoc analysis, separate and apart from what is the appropriate error term for the factors. Now, an additional option down here, let's call it 2A, is if we have normality of the treatment factor means, then we can draw probability pictures and answer questions about probability things such as confidence intervals, and probability of occurrence. If you do not have normality, then can't do that, but you can do this. And as a matter of fact, once we got past the two-way random design, we quit trying to do these things down below. We haven't even talked about those. We've just calculated the importance and gone on with our business. There was yet, so there were the new things. Number one thing was the AET stuff. Number two, I've already got that. Number two is the post hocs. And number three, it's obvious, I just slipped my mind just a second. It'll come back to me. Oh, it came back. We do normality, then location, and dispersion only if total is less than 25 the total percent of explained variable is less than 25%. It's the only reason we do dispersion, is to try to find out. In other words, we're so unfortunate as to have not found a large amount of variability that's explained. So now we're going to try to do everything we can, so we'll do a dispersion analysis just to see if we can get something. And the reason for that is the nature of the designs and the results that come out of the analysis of random effects designs is that if you get a reasonably large amount of explained variability, if you do a dispersion analysis, you ain't going to get that much. So it's not worth spending your time unless the total amount of explained variability going in is really low. It's just a pragmatic issue. Now, when you do this, of course, there are special formulas for the percent of explained variability. And those things are based on, we've got to compute the estimated variances in order to get the percent of explained variability. The software, the manual lays that out, and you do it for each piece of source of variability in the source table to add them together to get the total, and you're familiar with us having done that. Okay. We then moved on to IU8, and we'll take a break. My little clock right here says 7 o'clock. Right there. And since I've cheated you week after week after week after week out of breaks, let's take a break. Do you want me to start the timer, or do you want to just come back in 10 minutes? Well, when this little guy says a quarter after, we'll come back. Is this helping anything, or is this just like wasting time? You'd have been better off to stay home and study something else? What's that? Yeah, I want things. Interestingly enough, we go from 5005 to 5900, right? And then 5900 kind of goes like that. And then we come to this class, and it's a step up from 5900. And then this thing goes like this. And we're way out here. And then when you go to three-factor designs, it goes like that. And I want to make sure that you have a good, clear focus perspective on what we've got now, because we get into Unit 10 on three-factor designs, all in one big, fat lesson, one big block. We do fixed and crossed. We do random and crossed. We do mixed. We do mixed and nested. So we do it all together, all in one big chunk. Pardon? I don't remember. I don't think we do blocked. I don't think we do blocked. But it turns out when you have two random factors and only one fixed, things get really more complicated. So as soon as you start adding random factors, things just start getting wacky, wacky, wacky. And I wanted to make sure that you had a chance to kind of consolidate and get this stuff into a good perspective before we jump into the next one. Okay, I'm going to take a short break myself. I will be back. use it. slowing this thing down. Okay, IU8. Two-way, mixed, crossed designs. Crossed, that means we have, well, the two-way says we have A and B. Crossed says we have the interaction. Mixed says one is fixed, one is random. And again, we always have specimens, which is a random factor nested within the design cells. That only makes a difference if you have a blocked factor, otherwise the design cells are the treatment factor combination cells. When we have significance, we always have to do post hocs. We have post hocs to do on the random factor and on the fixed factor if it's significant. If they are, whatever's significant, we do the post hocs on. And obviously, in this particular case, we could have the interaction between the random and fixed factor significant as well. Now, here's where things get a little bit interesting. With fixed factor design, with fixed factor in a design, if the random factor is significant, then we learned a rule way back, the pledge rule, way back here. Maybe I ought to make a point of this. We had a pledge. Do you remember what the pledge is? The pledge is
The
that...
honor is,
yeah, on Kirk and Weiner. I will never assess the influence of one factor by collapsing across the levels of the other factor when that other factor is fixed. Rather, I will evaluate the influence of the first factor within each of the levels of the other factor. Now, when you have fixed design and two factors, you might have to do the assessment of A within B, and then you might have to turn around and do the assessment of B within A in order to find out what's going on whenever there's an interaction. Right? If there is no significant interaction, then you can collapse across and not have to worry about it. So that pledge comes back to get us in an interesting way. For just a moment, let's consider that this guy is not significant, this guy is significant, and this guy is significant. Well, with the interaction not being significant, there is no interaction to worry about. If the random factor is significant, then we have to ask ourselves the question, does it make any sense to consider the levels of a random factor by collapsing across the levels of the fixed factor? In other words, let's say we have fixed level 1, fixed level 2, fixed level 3, fixed level 4, and we have random factor level 1, random factor level 2, random factor level 3, and random factor down to level K, because that's the second factor. Does it make any sense for me to get the R1 average and the R2 average and so on down to the R sub K average and try to figure out what's going on across the levels of the other of the fixed factor? And the answer generally is no. By collapsing across that factor, we're missing out on certain things that we would want to know. And so we're always going to, and this is what's odd, even though there is no interaction, we're still going to look at the random factor within the levels of the fixed factor. Now, if there's an interaction, that is particularly true, but if the interaction is not significant, it's probably also a sensible thing to do. So, in both cases, we're going to estimate the variance for the factor, whatever it happens to be, and then go on and calculate the importance, which is the intraclass correlation coefficient. It's written both ways in the text, which is the percent of explained variability. Okay. Now, when it comes to assessing the fixed factor, we have to figure out whether to use an equal variance or an unequal variance procedure. And this is where things get dicey. These things get complicated primarily in the post hoc analysis. In the ANOVA, it's not that big of a deal. But while we're speaking about it, we have AB, and residual. Fixed, random, random, random. The residual is the appropriate error term for AB, and the residual is the appropriate error term for B. The AB interaction is the appropriate error term for A. Now, you can generate that with the expected mean squares. I don't necessarily expect you to have that memorized. You can generate it with MVP stats. When you do, this is what you'll find. As a result, the F ratio for A is equal to the mean square for A divided by the mean square for AB. That would have been evaluated in order for us to determine whether that fixed factor is significant. Now, in order for us to actually get to that point, we have to treat these factors as fixed, all factors fixed and crossed. The very first way we learned to do the ANOVAs. And then, based on the expected mean squares calculations that come out of MVP stats, we take that source table, we copy and paste it into Excel, and then we go in and create the proper F ratios based on the appropriate error terms that the expected mean squares routine gives us, and that's what I just outlined for you right there. Okay? So there's a little bit of work that you have to do to get there. And then we need to find out, since this is fixed, we want to find out which is better. Or which is best. Or where the difference, who is different from who else. And in order to do that, we have to figure out whether we should use an equal or an unequal variance approach. Now, this equal and unequal variance has to do with the appropriate error term. And we have learned that mean square AB is equal to the average of mean square A within B1 and the mean square of A within B2 and the mean square A within B3 and so on, all the way down to the mean square of A within B sub K. And it is these guys right here that we have to test for equal variability. Because the average of all of these guys is equal to that guy, the same way in which even way back to a one-way or the simplest two-way, let's go back to, let's consider a regular two-way fixed factor design. We have the variance within cell 1, the variance within cell 2, the variance within cell 3, the variance within cell 4, the variance within cell 5, the variance within cell 6. Now, if that were a one-way strung out as 6, same thing applies, okay? Now, I'm trying to find out if these cell variances are equal or not. And we have ways to do that. We call it a dispersion analysis, okay? And when we do, if we find that that's equal, if equal, then average of all cell variances equals mean square within. If not, then you have to use the separate individual variances in your post hocs. You might have to average them. This is for the fixed design. Well, the same concept applies here, except now we're wanting to find out if these cell variances are all the cell variances equal. Now we're asking the question, are these equal? Are these variances equal? And so the first thing we have to do is to create them. Now there's two things going on here that caused you, how many of you missed question number 37 on the homework assignment for this one? It had to do with if we have such and such equal variances, an equal variance approach would be used if or whatnot. It was a true-false statement. And the correct answer was keyed as false, which meant that you should go off and do an unequal variance post hoc. There's a way to have done it to get the true, and you'd have gone off and done a Tukey. And I'm going to kind of address that here. Brooke, this is for you in particular. She sent me an email about that. So what we have to do is to test these guys to see if they're different. And the way we do it is we take the smallest mean square AB sub K and divide it into the largest mean square A within B sub K. And that's an F, and we do that. So now all we have to do is to isolate how do we get those guys. Now, when we had the content material, the text material, the fixed factor had 3 levels. And so we did 1 versus 2 with 3 out. We did 1 versus 3 with 2 out. And then we had 2 versus 3 with 1 out. That's what was in the text material. And there were 2 things that fell out of that. You may not remember it. This may trigger something for you to go back and look at it. But there were 2 things there. One of them said, well, we could actually do these post hocs of the random factor within the levels of the other factor. Oh, I'm sorry, we're doing the fixed factor now, right? We could do the assessment of this guy, of the AB within the first one, and then do the same thing within the second one, third one, the fourth one. And so we came down and we did a series of one-way ANOVAs. I'm sorry, a series of two-way ANOVAs. On two levels. Yeah, because these are levels, right? Level 1 and 2 with level 3 out, level 1 and 3 with level 2 out, etc. On two levels, and we did all pairs, a series of all pairs of those guys. And then we used that to create this F ratio and determine whether or not we had equal or unequal variances. If this F ratio is significant, then we have unequal variances. If it's not significant, then we have equal variance, and then we can just use this term, the overall term, as was used in the first place. But in order to do that, we then took these one-ways, we took the mean square AB from each of those, and we did the ANOVAs on these to compare the levels of 1, 2, 1, 3, 2, 3. And then we also then used this when we found a significance. Then what we had to do, that's within B1, mean square A within B2, and so on, mean square A within B all the way down to K. And we had to get a weighted proportional variance to use as the variance, the unequal variance per level. And this was that special Excel spreadsheet to do that. Okay, now I think I probably did you a disservice by not giving you enough advanced warning on this part of it. But I want to stress again that these two-way ANOVAs were done for two reasons. Number one, as a post hoc per the Bonferroni approach. And number two, to figure out what the unequal variance ought to be used so that when we go to fast TM, we put in the means, we put in the variances, and we put in the N. These guys right here are what go in there. And we can only get those by doing the two ways at two levels of each factor. All pairwise of two levels. Okay? And if it was not clear to you that there were two reasons for doing these post hocs, you may have missed out on a part of this that ends up being important. So let me move forward now to the homework for Unit 8. We had the fixed factor had 4 levels. The random factor had 5 levels. And it turned out this guy was significant, and we have to do post hocs. Now, the post hocs for this guy, significant if it is to estimate the variance for the treatment factor, and then to calculate the intra-class correlation coefficient, that is the rho sub I, which is equal to, so let me just do it this way to make it explicit to kind of help a little bit. For example, the intraclass correlation coefficient for the random factor equals the estimated variance for the random factor divided by the total of the estimated variances. This guy is the sum of the estimated variance for A, plus the estimated variance for B, plus the estimated variance for the residual, and the estimated variance for the interaction. And if that interaction had to be broken down, then we had the pieces that we added up. Okay? Now, all of these things are done according to Kirk's recommendation. And even though we have A as a fixed factor, we still calculate its importance using the formula in order to put in here. But in the source table, A fixed, B random, AB random. This guy is calculated as omega squared. This guy is calculated as rho sub I. This guy is calculated as rho sub I. Just want to make that distinction clear, that this guy is a fixed factor and we calculate using the omega square. And that is the sum of squares for A plus the degrees of freedom for A times the mean square AB, because AB is the appropriate error term for this source of variability. Then that's divided by the sum of squares total plus 1 unit of mean square of the appropriate error term AB. You can use MVP stats to do that, or you can do it in your spreadsheet. Either way is perfectly fine. So we do this calculation right here, and these variances, by the way, the estimated variance for A is equal to the mean square for A minus the mean square of the appropriate error term divided by, since we're doing this for A, you have to keep track of the subscripts, A, B, and S. A has a subscript J, B has a subscript K, and S has a subscript N, where these things represent the number of levels. J, in this case, has 4 levels. In this case, K has 5 levels, and the specimens are how many ever the specimens are. Now, this is a universal rule. It's very important. It always applies, and it will help keep you out of a lot of trouble. Downstairs, you have to take this guy and divide it by the number of levels of the factor that you're not focusing on. Here I'm focusing on A, so downstairs has to be J and K. The J subscript is tied up with the mean square of the A's that I'm computing. Now, if I were going to do the estimate of the variance for factor B, that would be mean square B minus the mean square of its appropriate error term divided by N times J. Because here we're looking at B. B is subscripted by K. K is taken care of, so I don't need it. I have basically the downstairs is always NJK. And then you knock out the thing that you're dealing with. So I'm dealing with B, so I knock out that guy. And this is the mean square of the appropriate error term. If I'm looking for the interaction, AB, it's the mean square for AB minus mean square of the appropriate error term, whatever it is, divided by NJK. Now, AB is being dealt with, so that takes out the J and it takes out the K. And the last one is the variance of the residual. That's the mean square residual, and that's it. There is no error term for it, so there's nothing to subtract. And downstairs, I'm taking into account the residual involves specimens within A and B. They're all three taken care of. There's nothing to divide. And then you add all of these guys up, including this guy. You add all of them up to get the total. And away you go. So for the fixed factor, you do have to use Kirk's formula as if it were a random factor, only because it plays a part in the total. But when you actually come to computing its actual importance, you actually compute omega squared for the fixed factor. That's always true. Now, I came over here to do this. For this fixed factor, this guy is mean square. Dang it. I have this habit of writing over things 100 times, and it only makes things worse with these things. Mean square for A, let's call this A and B. Mean square for A. What the hell am I doing? Divided by mean square AB. And that's true. Then let's say that it's significant, so I've got to do my post hoc. In order to do the post hoc on this guy, I have to answer the question, equal variance or unequal variance, right? Just like on the previous page, just like the in class. So in this particular case, now, earlier I said there were two reasons for doing two-way, but there's two ways to do them. There's two reasons to do them in two ways. Let me talk about the two ways. Number one, I can do pairwise. That is, I can do 1 versus 2 with 3 and 4 out. 1 versus 3 with 2 and 4 out. 1 versus 4 with 2 and 3 out. Then I can do 2 versus 3 with 1 and 4 out. I can do 2 versus 4 with 1 and 3 out. Then I can do 3 versus 4 with 1 and 2 out. That's all pairwise. Okay? And when I do that, I'm going to get a mean square AB for each of these. Right? Now, if I take the maximum mean square AB and divide it by the minimum mean square AB in an F ratio, then that's going to tell me whether I can consider these guys all to be equivalent or not. This mimics what we did in the lecture material. And when you do it this way, it turns out that this F ratio turns out to be something in the neighborhood of 28.432 or something like that. It's a great big number. And you come to it leads to the conclusion that I have unequal variances, and hence I do Games and Howell post hoc. But in order to do that, then I have to use my little magical spreadsheet to take all of these guys and do the weighted, I have to do the weighted proportional assessment. And that thing kind of backs into reducing it down to 4 levels based on a consolidation of these terms. Now, there's another way to do it, and it's the way that I kind of led you down the path to do in class, especially given the spreadsheet, and it has its own flexibility. So what I could do is I could do a 2-way with levels of the fixed factor. There's always the fixed factor and the random factor in. The number of levels of the fixed factor are 1, 2, and 3 with 4 out, 1, 2, and 4 with 3 out, 1, 3, and 4 with 2 out, and 2, 3, and 4 with 1 out. And from those, I will get a mean square between, or AB. I'll get a mean square AB. I'll get a mean square AB. And I'll get a mean square AB. Now, obviously, I can take these guys, put them into the F ratio with the maximum mean square AB and the minimum mean square AB. And when you do that, that F ratio turns out to be something like 2.98. And it turns out that it's not significant. That would lead you to do Tukey test. The item number 37 on the homework assignment was keyed to have done it this way. But I think in the lecture and the way I presented it, it kind of led you down this path to do that one. So I'm going to go in and for item number 37, give everybody credit.
So is the first one considered more appropriate then?
I've been doing a lot of thinking about that. Well, not a lot. I haven't done enough thinking about it. I've done some thinking about it. And as we look at the analogy with what happens with the regular 2-way, let me go back to here. For the regular 2-way, we have these cell variants, right? A cell variance, 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 a cell variance. And this is all of the individual cells of the design. And if they're significantly different, and we have to come back, so let's assume that this is factor A level 1, factor A level 2, factor B level 1, B level 2, B level 3. And let's say that B is significant, and now I have to do a post hoc. See, if A is significant, I don't have to do a post hoc because there's only 2 levels. But if I have to come back and do a post hoc because B is significant, then what I'm going to have to do is I have to take these 2 guys and get the average variance for B1. And then I have to take the average of these cell variances for B2. And I have to take the average of the variances for B3. And those are the guys that I put into FAST-TM. But notice it is the average of the cell variances. So by analogy, logically speaking, it would be, we would have to leverage these things up I would have to average these guys up in order to get the weighted proportional means. And when I come back with these weighted proportional means, there's 4 of them. There's 4 of them. And the second part of that spreadsheet, down below the top part, allows you to put in pairwise, and it will end up combining them. You just have to put them together in the right way. Okay? Now, the good news for us here tonight is this. I suspect that all of you probably did it this way, and you went off and did a Tukey post hoc. Did you? Do you remember?
Yeah, I did.
It went that way.
Yeah, I think everybody probably did it that way. There's probably one holdout like Josh or somebody else might have done it on a pairwise basis, because I did not remember when we were in class, the factor had only 3 levels, and so doing all pairwise was all of the possible combinations that we could possibly do. Okay? It's the only way we could do it. When we got over here to when you have 4 levels of the factor, then if you do pairwise, there's 6 of them. If you do it just on the 4 out, 3 out, 2 out, 1 out, there's only 4 of them to do. So that's wherein, and I'm beginning to think that this is the more appropriate way to do it. I just need to think a little bit more about that. The good news, however, is this. If you did it this way, as most of you did, and did a Tukey, you find a certain result. If you had done it this way and done a Games and Howell, it turns out you get exactly the same results. Now, that will not necessarily always happen. But for us, so the conclusions and the downstream side of that would all be the same. The point estimate groups would be the same. The approximate estimated variances would all be the same. Doesn't really matter. The solutions, when was that homework assignment due?
Yesterday.
Yesterday? What's today? Tuesday. Yesterday. It was due yesterday, right? I'm updating, and I think I hid the solutions because I was updating them. So I will unhide the solutions, and you'll see it done both ways. You'll see both ways in the solutions. But in answer to your question, Matt, I think actually this pairwise is probably the most correct way to do it. Now, the other thing I want to tie together here is I said that there were 2 ways to do it. This is the first way and the second way, but there are 2 reasons to do it. Okay? 2 reasons. And so, let me clear out some space here. Reason number 1 to do it is to get estimated group error variances. This is all of that stuff. Either way that you do it, you're still trying to get a group variance for a variance estimate for each group so you can do the post hocs using an unequal variance approach. For error variances, for unequal variance approach. Determination. So we're trying to determine the unequal or the equal variance approach. Reason number 2 is when we do these analyses, we're really doing pairwise comparisons. Especially if you're doing it this way, it is the equivalent of Bonferroni pairwise comparisons. Because when I do this and I get statistically significant difference, it says that level 1 is different from level 2. In the ANOVA that's using this guy as the error term, the numerator part for this 1, 2 is doing a pairwise comparison between those 2 levels of that factor, and these 2 levels, and those 2 levels, and these 2 levels, and these 2 levels, and these 2 levels. Now, here's where I have my trouble with this. Dr. Luftig is no longer around to talk to about it, so I just have to think through it myself and then do what I think is best. And that is, when you read the text material, it's doing this in the context of a Bonferroni. And when we use Bonferroni, we control the type 1 error rate, alpha, by dividing by C. Right? Now, if you have 4 means, 4 levels, you're trying to do all possible pairwise among 4 levels. How many pairwise comparisons are there? Well, 4 times 3 over 2 equals 6. And there they are. Now, here's the question that I would ask. Why would you ever do all possible pairwise tests using the Bonferroni control for alpha? It's too conservative. Bonferroni is always too conservative when you do all possible pairwise. And so this reason, when you have 3 levels, there's only 3 pairwise comparisons, all possible versus Bonferroni control, there's virtually no difference. But when you start getting 3 or 4 or 5 or 6 levels, then it gets to be a big deal, and there's no reason you would ever want to do this for option number 2. So that's the thing I haven't resolved for myself yet. But it is clear to me, just based on this class example alone, excuse me, when you do this approach, the F ratio is 28 and is significant. When you do it this way, the F ratio was 2.98 and was not significant. And so, since we're about the business in this program of teaching you conservative statistics, I would say it's probably best to err on the side of doing an unequal variance approach than it is an equal variance approach. Now, as I started out at the very beginning of the night, way back on slide number 1, well, not slide number 1, slide number 1 of the discussion, this one. The post hocs here were always very straightforward and very clear. There wasn't a lot of jiggling around we had to do, although at the time we were learning about it, it was hard enough to figure out. But once we figured it out, the difference between Bonferroni and Tukey was pretty straightforward. And the way I talked about how this was developed as equal variance or unequal variance approach, Tukey versus Games and Howell approach, it was easy for software companies to incorporate the Tukey procedure into their software, and SPSS did that. And since this course was erected utilizing SPSS as the software tool, that was incorporated into the logic and the thinking and the teaching of the course. That way you can click Tukey. When we get up to these higher level designs, and once we move away from SPSS to R, for example, we're left out on our own to figure out how to do the post hocs. Now, if it weren't for fast TM, we would have to do them on our own by hand. That's why I used to have to do them in graduate school. And that's why I wrote a little program to do a little Excel spreadsheet to do pairwise comparisons using all the different methods, and you can just pick the right one. But for us, since we're using fast TM, either for a Tukey, for these designs, two-way and higher designs, we're not using any software that can do it for us. So since we're using fast TM, we have to compute the cell means for the main effects. We have to get the sample size for the cell means. And if we're using Tukey, we have to get the error term off to the side, like I explained over here. When we're using Tukey, we're going to get the mean square off to the side over here, and we have to enter the means. We don't have to enter the variances, but we do have to enter the sample size. If we're using Games and Howell, then we have to enter not only the means, yes, we have to enter those. Sample size, yes, we have to enter that. Now we also have to enter the variances, but we don't have to enter this stuff over here. So it's only the extra little step of calculating what those variances are and sticking them in there, and then we're going to use FastTM to do it all anyway. So for us, in where we are, there's really no big difference between doing a Tukey or a Games and Howell. They're just about as easy, they're just about as difficult for a given design. So with that in mind, when we are here, doing it this way, now I'm running out of colors to make emphasis. When we're doing it this way, we have more of a likelihood of detecting significant differences in variances than if we do it this way, because when we're doing it this way, think about this. When I do this guy, I'm averaging across a couple of these guys. When I'm doing this one, I'm averaging across some. When I do this guy, I'm averaging across. When I do this, I'm averaging across some of those other terms. And when I start averaging, I hide variability. So if I do it this way, that is with just throwing one out at a time, if I do it that way, I'm less likely to find significant differences in the variances and less likely to do an unequal variance approach, which probably is not the most appropriate way to do it. So back to answer Matt's question a third time to emphasize it, is the most appropriate way to do it is in fact this way, because it's no more difficult to do Games and Howell than it is Tukey. But we still have to take these guys. See, this is the thing that I have to resolve for myself. I still have to take these 6 analyses, and I'm going to whittle them back down to give me 4 of these means to put in the table, because I have 4 levels to deal with. So I just wanted to point out that that's the thing that we have going here. Oh, and it's 8 o'clock. Okay, let me just give you a thumbnail sketch for Unit 9. Not IU9, but Unit 9. Unit 9 was a 2-way mixed nested design. So with that we have A, B, within A. And it is almost always that the nested factor is random, and we always have specimens, which is a random factor, specimens nested within AB, almost always. Since this guy is a random factor and this guy is a fixed, we have the same kind of issues. The ANOVA is going to be A, B within A, specimens within AB. This is the error term for that. This is the error term for that. This guy needs to be broken out, B within A1, B within A2, B within A3, and so on, down to B within AJ. Now, it makes no sense at all in a nested design to look at this effect right here, the B within A overall. We need it, however, because this term is the error term for A. So you have to do that analysis first. Then you have to take this guy and break it down with a bunch of one-ways. These are one-ways of B within A, and this is a random